In this video, we are going to discuss a few questions from your pre-PSPM for SP015 set 2. So I've singled out 9 questions, which more than half of you got it wrong, and I'm going to discuss this question one by one. So let's look at the first question. A plane flies from London Heathrow Airport to Dubai International Airport, a distance of approximately 5,500 km at an average speed of 1,200 km per hour. Okay, so this journey is from London Heathrow Airport to Dubai International Airport. So there are two positions of interest, and the distance between these two airports is 5,500 km, and you are going to travel from Heathrow to Dubai International Airport at the speed of 1,200 km per hour. Okay, then after you reach Dubai International Airport, you return to London Heathrow Airport, and the return trip was made at an average speed of 1,050 km per hour. So the to and the fro journey have different average speed. That's the issue. And now they ask you to find the average speed of the whole journey. Okay, so let's try to visualize the situation here by drawing a very simple diagram. We know we have London Heathrow. Okay, so this airport is in UK. Then you have another airport which is called the Dubai International Airport. So let's call it Dubai Airport. Okay, so you know that the distance in between them is 5,500 km. And you are going to go from London Heathrow towards Dubai Airport. Then once you reach there, after that you go for a return journey from Dubai Airport to London Heathrow back. Okay, so the to journey from London to Dubai, it's 1,200 km per hour. That's the average speed for the to journey. For the fro journey, it'll be from Dubai to London Heathrow. The average speed is 1,050 km per hour. And they now ask you to find the average speed. And the average speed, I believe you see that the unit is in meter per second. So later we need to do some conversion also. So we know the average speed, V average, is equals to the total distance traveled divided by the total time elapsed. Okay, you can just call it as time elapsed. You might be wondering whether average speed is just average velocity's magnitude. No, okay? Average speed is not the magnitude of average velocity. They are different things. For velocity, you are calculating it based on displacement over time. But here, for speed, you're calculating it based on the distance traveled divided by the time elapsed. Okay, so need to be very clear what is average speed, what is average velocity. So the total distance traveled, we know that it's a to and fro journey, so it's 5,500 km for the first part of the journey. The second part of the journey will be 5,500 km as well, because they travel the same path, just in opposite direction. So you know that the distance will be 2 times of 5,500 km. Okay, then after that, the time elapsed. So I'm going to find the time elapsed. Well, you can do it on the side, find the time taken to travel the first part of the journey and the second part of the journey. You can do it on the side, then substitute it in. But you can do it right away inside here as well. What you can do is, you know that the time elapsed will be the distance traveled for the first part of the journey divided by the speed, average speed for the first journey, plus the distance for the second part of the journey divided by the speed of the second journey. Okay, the idea is like this. We know that the first part of the journey, you can find the average speed by taking the distance traveled for the first part of the journey divided by time. Okay, so if you want to find the time, what you need to do is just bring the distance to the left hand side, then you get d1 over v1. So the same idea will be for the second part of the journey. The average speed is v2, so it's distance for the second part of the journey divided by the time elapsed for the second part of the journey. So if you shift it around, you know that t2 will be equals to d2 over v2. So if you want to find the total time elapsed, that will be t1 plus t2. And how do you get t1 plus t2? It's just d1 over v1 plus d2 over v2. So that's what we do inside here. Okay, so now let's perform a bit of substitution. 2 times 5,500 divided by this one, distance travel is 5,500. The average speed for the first part of the journey is 1200 plus the second part of the journey, you have the same distance traveled, but your velocity will be different. Your average speed will be different. So if you calculate everything here, I believe you get 1120 km per hour. So what you need to do now is just do unit conversion. You know that 1120 km per hour can be written as 1200 km per 1 hour. So you want to eliminate the km, so you know that km should be at the bottom. You want to convert into meters, so meters should be on top. Next, you want to eliminate the hour, so you should put it on the opposite side. The hour was previously at the bottom of the fraction, so you need to create an hour on top of the fraction. Okay, you want to convert it to seconds, so you put second over here. So you know that 1 kilometer is equals to 1000 meter, and you know that 1 hour here is equivalent to 60 times 60, 3600 seconds. So if you perform your calculation, this conversion here, I believe you should get an answer of 311.11 meter per second. And with that, we know that our answer is C. Okay, you can do it separately. What I mean is you can perform your calculation here to get T1 and T2, then add them up, put it inside here, then only perform your second part of the calculation. But usually I prefer to jumble up everything in one calculation, because if you perform two separate calculations, you need to round off before you bring it in, right? So the process of rounding off might cause a problem. Of course, you can just keep all the values you have in your calculator and continue to add them up over here. That's a better choice of doing it. But for me, I usually just put all the values inside here, then just calculate it once to get the answer. So the answer is 311.1 meter per second. So that's how you solve question 2. Let's move on to the next question. Question 4. A ball is projected with a velocity of 10 meter per second at an angle of 30 degrees with the horizontal surface. What is the speed of the ball after 1 second? So let's try to draw a diagram to illustrate the situation here. We have a horizontal surface and a ball is being projected at an angle of 30 degrees, and it has an initial velocity of 10 meter per second. So we know this is a projectile motion because once the ball leaves the horizontal surface, the only force acting on it is the gravity. So projectile motion are motion which is only influenced by the force of gravity. So this is a projectile motion, and we know that you trace a parabolic path in this case, something like that. Okay, so this is the situation we are facing here. Now they ask, what is the speed of the ball after 1 second? So the ball will travel through this parabolic path, and they are interested in the speed of the ball after 1 second. So we don't know whether 1 second is over here, or over here. Never mind. Let's proceed through the 5 steps that we usually do to find the answer. Okay, the first step that I usually do is I visualize the situation. Okay, so when I visualize the situation, I put in all the values I have, all the information I have into the diagram. It will make my calculation later easier. So the second part of it is I determine the initial and the final position. It's important for me to determine the initial and final position before I start doing any calculation, because it will help me to identify my SUVAT more clearly. Okay, so we know that what they are interested in is the speed of the ball after 1 second, but we don't know exactly where is the position of the ball after 1 second. So what we do, we just simply assume a position. Okay, so we know that the ball definitely starts from the horizontal surface. So this point here will be our initial position. Where is the ball at the end of 1 second? We don't know, so let's just simply pick a point. Okay, if you don't know, just simply pick a point. Let's call it the final position. Okay, we don't know whether it's going, whether it has passed through the maximum height already. We don't know it's at the first portion of the rising part of the portion or the falling portion. So you just pick point. Later it will correct itself based on the value of velocity that we obtain. Okay, so this is initial and final. We have determined it and we label it in the diagram. The third part, what we need to do is to determine the SUVAT based on the initial and final position. Based on the initial and final position, your initial and final position is based on the question. So when you do find your SUVAT based on the initial and final position, you are finding your SUVAT based on the question. You see how it works step by step. Okay, so in this motion here, it's a 2D motion. So what we need is an X component and a Y component. So X component will have its own SUVAT. We call it SUVAT. Then Y component, of course, it will have its own SUVAT. Okay, T is of course not a vector, so there's no X or Y component. It's a scalar, so there's only time. So it's universal for X and Y component. They are using the same, they are traveling on the same timeline. Okay, so Sx will be the distance from the initial to the final over here. So do we know this distance over here? We don't know, so that's why we put it as a question mark. Ux will be the initial velocity x. So what we do is we look at the initial point is over here, look at the velocity to find its x component. So what we need to do here is we need to resolve it into its x component and y component. Okay, so this one will be ux, this one will be uy. Okay, so we know that it will be a cosine here in order to obtain the x component. So this will be 10 meter per second cosine 30 degree. We know that for projectile motion, the speed in the x component should remain the same. The speed should remain constant throughout the whole projectile motion. So the x component, you should expect the final and initial to be the same, and that is because there is zero acceleration happening in the x dimension. Why zero acceleration happening in the x dimension is because there is no net force acting in the x dimension. There's only one force acting in this situation, which is the gravity, and gravity is in the y dimension. That's why the acceleration is happening in the y dimension, not the x dimension. So the x component acceleration is of course 0 meter per second squared. So the time is 1 second. That's what they ask. The time is the time taken to go from the initial to the final. What is the amount of time elapsed to go from initial to final? 1 second. Okay, so now let's move on to the y component. Sy will be the displacement from the initial to the final in the y component. So this is Sy actually, but we don't know much about the final position, so we cannot determine Sy as well. Uy we know is the y component of the initial velocity. Initial velocity is here, y component is this one over here. So we know that in order to find uy, we need to use sine, okay, because it's on the opposite side. Okay, so this will be 10 sine 30 degree. Do we know the final y component of velocity? We don't know because we don't know where is it even. So it's difficult to determine the y component of velocity now. So we just leave it as blank. So we know that for projectile motion, the y component of acceleration is negative 9.81 meter per second squared. This one is fixed as long as you are near the surface of Earth. That's the idea for projectile motion. The projectile motion, the only force acting on the ball, it's the gravity. Gravity is just mg if it's near the surface of Earth. So if you do your acceleration, weight is equals to ma, so mg equals to ma, so a equals to g. So that's why it's negative 9.81 meter per second squared. Okay, so now we have all the values already. We move on to the fourth step. The fourth step is to pick a suitable equation to determine what we want. Then from there, we substitute and obtain answer. The things that we want is the final speed. So we need Vx and Vy. We have Vx already. What we don't have is Vy. So in order to determine Vy, we need to use the information that we have. We have U, we have A, we have T. So we have been given 3 information in the Y component, and we want to find the final Y component of velocity. So that's doable. You need an equation that has U, V, A, and T inside. And the equation should be V is equals to U plus A, T. Okay, it has the U, A, and T that is given in the question, and it has the Y component of velocity that we want to determine. So what we need to do now is just continue with substitution and find answer. Usually I call it the 5th step, but I just call it, okay, 5th step is just to do substitution and obtain your answer. So this one is 10 sine 30 degree plus negative 9.81. The amount of time elapsed is 1 second. So if you perform your calculation, I believe you should get the answer to be negative 4.81 meter per second. So this is the Y component of velocity. We still need to find the actual velocity, the magnitude of velocity. Only we can know that the magnitude of velocity is speed. Okay, so we need to combine our Y component of velocity with the X component of velocity in order to obtain the magnitude of velocity. So the magnitude of velocity is called V. So in order to obtain this, you know that it's Pythagoras theorem. The X component of velocity plus the Y component of velocity, not plus, I mean Pythagoras theorem. So you perform a calculation. This is 10 cos 30 degree square plus negative 4.81 square. So if you perform a calculation, you get that it's negative 4.81. Negative 4.81. For Pythagoras theorem, you know that the answer should be positive. Okay, because this is magnitude of a velocity, magnitude of a vector must always be positive. 9.91 meter per second. Okay, so this is the magnitude of velocity. And we know that magnitude of velocity is just equivalent to speed. That's why this will be our answer. So answer should be 9.91. Okay, if you are interested to determine the direction, what you need to do is you look at Vx. Vx is a positive value. So that means the X component of velocity is pointing in the X direction. The Y component of the velocity, it's a negative value. So because it's a negative value, it means it's pointing in the negative direction. So we set our positive direction in the Y dimension to be positive up, negative down. So the answer for our Y component of velocity is negative. That's why it's pointing down. So this will be Vy. So if you combine them, you get the vector for velocity over here. And if you want to find the angle over here, what you need to do is just do your tangent theta equals to Vy over Vx. Then you find your angle later. Then you need to describe your angle, whether it's above or below. In this case, it's below. And to describe whether it's positive side of the x-axis or negative side of the x-axis, this is on the positive side. Okay, think of it as an axis like this. So this is the positive y, this is the negative y, this is the negative x, this is the positive x. So this is below the positive x-axis. Okay, you can do the calculation yourself. This is not required in this question, just to elaborate on it. Okay, so that's how you solve question 4. Let's move on to the next question. Question 8. A car of mass 1,200 kg is connected by a tow rope to a truck of mass 2,800 kg. So this truck here has a mass of 2,800 kg, and a tow rope is connected the truck to the car, which has a mass of 1,200 kg. The truck tows the car in a straight line. Tows means like you are dragging the car along, okay, like what you see on the highway. So the truck is towing the car in a straight line along a horizontal road. So the truck is driving to the right, then the car follows going to the right. It's a straight line motion, not curving anywhere. Assume that the tow rope is horizontal. So as you can see in this place here, we assume this tow rope here to be horizontal. So it's not at an angle. A horizontal driving force of magnitude 3000 Newton acts on the truck. So because the truck is the one towing the car, that's why the truck will have to step on the pedal. You have to accelerate it. Then it provides a horizontal driving force of magnitude 3000. So the engine, the motor, everything provide a driving force of 3000 Newton on the truck, making the truck move with an driving force of 3000 Newton to the right. Okay, a horizontal resistance force of 800 Newton acts on the car. So this car here is experiencing a resistance force. So the car is moving to the right, the resistance should be to the left. So this resistance force is 800 Newton to the left and it acts on the car. Whereas the magnitude of horizontal resistance force that acts on the truck is 600 Newton. So the truck here also experiences a resistance force. Then because the truck is moving to the right, the resistance force should be to the left and should be 600 Newton. The resistance force is not the rope. The rope and the resistance force should be different thing. So the resistance force can be due to the air surrounding the truck and the car. It can be due to the surface irregularities, various factors. Okay, so the car and the truck accelerates at 0.4 meter per second square. So these two vehicles here, they are both accelerating together with an acceleration of 0.4 meter per second square. And you are asked to find the tension in the rope, this rope over here. Okay, so it's a relatively complex situation, I would say. So let's try to draw a free body diagram. Maybe not draw a free body diagram first. Let's label what we know in the diagram over here. We know that this car is 1200 kg. We know that this truck is 2800 kg. So we know that there will be a horizontal driving force on the truck. Let's call it an external force. And this external force acting on the truck, let's call it T, should be equals to 3000 Newton. Then there is a horizontal resistance force of 800 Newton over here, acts on the car. So resistance force, just now we discussed it to be opposite direction. So let's call it F subscript R to represent resistance, and this is for the car. That's why subscript again say it's for the car. And of course, the truck also experienced similar thing. There's a resistance force acting on the truck, and it should be 600 Newton. This one should be 800 Newton. Okay, now both of these car is accelerating at 0.4 meter per second. So the acceleration is 0.4 meter per second, and it happens for both the car and the truck. So this is the situation that we have now. Let's try to draw a free body diagram for both of the vehicle. We will draw a free body diagram for the car, and we will draw a free body diagram for the truck. Then it will make our analysis of forces later easier. Okay, so the car, when we want to draw a free body diagram, start by drawing a dot to represent the object, then drawing the axis accordingly. So the axis here, one should be usually following the direction of motion. So in this case, the x-axis will follow the direction of motion. The y-axis will be perpendicular to the direction of motion. Okay, so now we have this ready. Let's ask ourselves the 5 questions in order to fill out our free body diagram. The first question is, does the object here has weight? The object here is the car. Wait. The first question is, does the car has mass or not? So the car here, the object here is the car, and the car has mass 1200 kg. Therefore, we know that this car here must have weight. The weight, we call it weight of car. Weight subscript C, car. Next question is the car connected to any rope, strings, or cable? Yes, the car is connected to a rope actually over here. So therefore, we know that there must be tension. Tension must be always away from the object along the rope. So this tension here, I call it T because there's only one rope. I don't need to label it as different T. Okay, so it's away from the car along the rope. So this is the second question done. The third question is there any force being explicitly mentioned or being labeled in the diagram due to external force? Okay, so you can see here they explicitly mention that there's a resistance force acting on the car over here. So therefore, you should expect that this car here should experience a resistance force to the left. So this is the resistance force, FRC. Okay, then that's the force being explicitly stated in the question. Next, the fourth question, is the car in contact with any surface or not? Well, the car is in contact with the floor, right? So the car is in contact with the floor, therefore there should be a force acting by the floor on the car. What is the direction of the force? It's a normal force. Normal means 90 degrees, so you know that this normal force must be perpendicular to the surface. So if the surface is in the x direction, you know that the normal force should be in the y direction. So pointing up or down, again, normal force must be a push. So the floor is acting on the car. The floor is pushing the car. So if the floor want to push the car, it should be pushing upward, because downward will be pulling on the car already. So the floor is pushing on the car, so it must be pointing upward. So we will call this as a normal force acting by the ground on the car, by G, by the ground on car, C. Okay, so that's the fourth question. The fifth question is the surface in contact rough or not? Well, I believe it's a rough surface, because if it's not a rough surface, the car cannot move. But we already take into account the resistance forces over here already, so we don't need to think about it in terms of friction anymore. Okay, because I think this horizontal resistance force includes the friction that should be discussed now. Okay, since it's included in the resistance force, we are not going to think of friction anymore. Okay, so these are all the forces that are exerted on the car. Let's move on to the free body diagram of the truck. Again, we know that we need to draw our axis, x and y. Let's do that. Let's continue to ask ourselves the 5th question. Does the truck has mass or not? Yes, it has mass, therefore it will have weight, and call it the weight of the truck. Next, is the truck connected to any rope, strings, or cables? Yes, the truck is definitely connected to a rope over here, so it should be away from the truck along the rope, so it's pointing to the left. So tension away from the truck, along the rope, so it's to the left. So we know that this tension here, these two tension here, should have the same magnitude, because they are the same section of the rope. This is one rope, so the tension on the left hand side of the rope and the tension on the right hand side should be the same. So we don't label it as T car and T truck. They should be the same value. Okay, next, the third question is there any force being explicitly stated in the question for the truck? Yes, they explicitly mentioned that there's a driving force of 3000 Newton. So we know that there will be a driving force over here, force of the truck, which is 3000 Newton. And there's also a resistance force, which is force resistance acting on the truck. Okay, so these are two forces being explicitly mentioned in the question. Next, the fourth question is the truck in contact with any surface? Yes, the truck is in contact with the floor, therefore there should be normal force. The same way to determine the direction of normal force, you know that it's pointing upwards. This is by the ground on the truck. Okay, and lastly, is the surface rough or not? Yes, this surface is rough, but we have already taken into account the friction in the resistance force experienced by the truck. Okay, so these are all the forces that are acting on the truck, and this is the free body diagram of the truck. So we have now created the free body diagram of the car and the free body diagram of the truck. All we need to do now is to analyze the situation we have here. Okay, so all the motion here are happening in the x dimension, so we are probably going to focus on the x dimension. So that's why we are going to ignore the y dimension over here and focus only on the x dimension. We know that both of the car here are experiencing an acceleration of 0.4 meter per second squared. Therefore, you know that the right hand side forces should be more than the left hand side forces in order to create an acceleration. the force in the x dimension must be not balanced in order to have an acceleration. That is just Newton's second law. So we are going to analyze for the car first, then we are going to analyze for the truck. So we are going to analyze it using Newton's second law because it has an acceleration. So the sum of force in the x dimension for the car should be equals to the mass of the car times the acceleration experienced by the car. So the x dimension here should have tension minus the resistance force experienced by the car, and should be mc ac. Okay, this is the equation that we have for now. Then now we can do substitution, I think. So this one is T. The resistance force experienced by the car is 800 Newton. And the car is 1200 kg. And the acceleration is 0.4. Okay, so if you perform your calculation, I believe straight away you can obtain the answer. But it's more straightforward than I expect. Okay, so the answer is 1280. So the answer should be 1280B. Okay, to double check whether it's correct or not, what you can do is you can continue to analyze the x dimension of net force for the truck. Then you know that it will be equal to the mass of the truck times the acceleration of the truck. You should expect that if your tension is correct, you should generate the same acceleration as the result. So what we are going to do is we assume we don't know the acceleration, then we check whether we get the same acceleration as being stated in the question over here. So we're going to use our tension over here. So let's build the equation first. We know that it will be the driving force of a truck minus the resistance force experienced by the truck minus the tension. So we take the right minus everything on the left, and should be equals to the mass of the truck times the acceleration experienced by the truck. So we substitute all the value here. 3000, the resistance forces 600, and the tension 1280. We double check our answer. If our answer is correct, we should get the same acceleration for the truck as our result. So let's try to do a bit of calculation. Yep, the answer is 0.4 meter per second square. Therefore, you have double checked, it's correct. It's true. Okay, this is just double check. So the answer is 1280 Newton. Okay, there are many things that they can ask actually, but I think this is relatively simple compared to most of the multiple bodies question. Okay, usually when it involves multiple bodies, there's usually simultaneous equation involved. But in this case, it's nothing simultaneous, it's just direct substitution. Okay, so this is question 8. Let's move on to the next question. Question 14. What is the distance of a geostationary satellite from the Earth's center, given that the mass of Earth is 5.97 times 10 to the power 24 kg, the radius of Earth is 6.38 times 10 to the power 6 meter, and the mass of satellite is 100 kg. So they ask you the distance of the geostationary satellite from the Earth's center. So I believe the key part to solve this problem is to understand what is geostationary satellite. So geostationary, the word comes from geo. Geo means geographically. Stationary. Geographically at rest. Can I say it like that? I think you get the idea. So when we say a satellite is a geostationary satellite, that means it's geographically not moving. What do we mean is like, let's say you have a satellite on top of Malaysia. Okay, we have a satellite right above Malaysia. So if that satellite is a geostationary satellite, that means at 8 a.m., 12 p.m., 7 p.m., 11 a.m., whatever time you try to check the position of the satellite is always above Malaysia. It will never travel to Indonesia, it will never travel to Europe, anywhere. Okay, so geographically, the satellite is at the same position even though when time passes. That's the idea of a geostationary satellite. So if we draw an Earth, so let's say this is Malaysia. Malaysia, let's say, is over here. Okay, then the satellite is up here. Okay, so let's assume the rotational axis is like this. So if the Earth happens to rotate, then Malaysia ends up over here at some later time, then the satellite should also remain right above it. So that means that if the Earth is spinning with angular velocity of omega, then you know that the circular motion of this geostationary satellite should also have the same omega. So you know that omega for Earth and the omega for the satellite should be the same. Or else, if the Earth is rotating faster, then Malaysia will overtake the satellite. So Malaysia will run ahead of the satellite. If the Earth is slower, if the satellite is faster than Earth rotation, then satellite will overtake Malaysia. Then satellite will be going past Malaysia already. So it's not geographically stationary anymore. That's why to remain geographically stationary, the Earth and the satellite should undergo its rotation and circular motion at the same angular frequency or angular velocity. That's why the 2 omega should be the same. So you know that 2 pi divided by the period of the Earth's rotation should be equals to 2 pi divided by the period of the satellite circular motion. Therefore, you know that the period of the Earth rotation should be equal to the period of the uniform circular motion of the satellite. That's why if you talk about a geostationary satellite, you need to know that the period of the geostationary satellite is equals to 24 hours. That's the idea of geostationary satellite. The Earth takes 24 hours to finish one rotation. That's why the satellite should also take 24 hours to finish one complete circular motion. Okay, so geostationary satellite, that's the idea. So we want to find the distance of a geostationary satellite. We know that the period of the satellite is equivalent to this equation over here, 2 pi r cubed over g and m. So r here is the distance of the satellite from the center of the Earth. So we have to be very clear about that. It's not the radius of the Earth. It is the distance of the satellite from the Earth, from the center of the Earth. Okay, then the g over here is the universal gravitational constant, but the mass over here is the mass of the planet where the satellite is orbiting. In this case, the satellite is orbiting around Earth, so this will be the mass of the Earth. So the mass of the satellite will not be relevant for the discussion over here. It's only the mass of planet that affects the period of the satellite orbiting around the planet. So we know that this is 24 hours, but we do everything in SI units, so let's change it to second. So it's 24 times 60, 1 hour 60 minutes, 1 minute 60 seconds. So 2 pi, you're interested to find the distance, so leave it as r. The g over here is 6.67 times 10 to the power of negative 11. The mass of a planet is given over here, it's 5.97 times 10 to the power of 24. So these are all the information being given, and if you perform your calculation using calculator, you should be able to obtain the answer for r to be equals to 4.22 times 10 to the power of 7 meter. And if you want to change it into km or meter, because you see meter here it's power 7, so none of this is correct, so you have to change it to km. So if you want to change it to km, you know that 1 km is equals to 1 times 10 to the power of negative 3 meter. So if you do your conversion, you want to eliminate the meter, so you have to put meter down here, you have to put km up here. So km, 1 km is equals to 10 to the power of 3 meter. Make a mistake. 10 to the power of 3 meter. So if you do your calculation over here, you should get 4.22 times 10 to the power of 4 kilometer. The meter cancel out, so you get km. So we know the answer will be C over here. So the distance of the geostationary satellite from the center of Earth is 4.22 times 10 to the power of 4 kilometer. Okay, so that's how you solve this question 14 over here. So no matter how massive is your satellite, it's a 100 kg satellite, it's a 1000 kg satellite, it's a 5 kg satellite, no matter how light, how massive is the satellite, if you want it to rotate, if you want it to undergo circular motion around the Earth center in a geostationary way, you have to set it up to the same height. It's always 4.22 times 10 to the power of 4 kilometer from the center of the Earth. No matter how massive your satellite, if you want it to be a geostationary satellite, you set it up at the same distance away from the center of Earth, which is 4.22 times 10 to the power of 4 kilometer. Okay, so that's how you solve question 14. Question 17. A figure shows a displacement time graph of an oscillating ball. So we have a ball undergoing simple harmonic motion, and this displacement time graph here is trying to illustrate how the ball oscillates. So you are given the fact that the maximum velocity is 3.2 meter per second. So if you trace the velocity of the object and how it changes with time, you find that the maximum velocity that can be achieved by this ball is 3.2 meter per second. Now they ask, what is the velocity of the ball when the acceleration is 3 meter per second square? So you are given this graph here showing that this ball here starts from the equilibrium position, then move up, down, something like this. Okay, so let's try to extract all the information that we have from the question and from the diagram, the graph being given over here. So we know that for this graph here, for the question, you can see that the maximum velocity is 3.2 meter per second. That is the maximum velocity you can achieve in this simple harmonic motion over here. In the question, they also mentioned that the acceleration is 3 meter per second square, but you might think of it as information being given, but actually think of it as part of the question actually, because the acceleration of the ball undergoing simple harmonic motion changes with time. The acceleration goes from 0 to maximum, to 0 to the maximum in the negative direction, then 0 to the maximum in the positive direction. It keeps changing, but for certain moment, at certain position, your acceleration will be 3 meter per second square. And this question here is interested to find the velocity of the ball when the acceleration is 3 meter per second square. It's a specific moment, it's a specific position that they are asking for the velocity of the ball. And at that position or at that moment, the acceleration is 3 meter per second square. So I think of this 3 meter per second square here as part of the question, not a property of the simple harmonic motion itself. The Vmax here is the property of this simple harmonic motion, because if you measure this is the fact for the simple harmonic motion over here. If you track the velocity with time, you find that the maximum is 3.2 meter per second. No matter you trace it at earlier time or later time, you find the same answer. Okay, but this acceleration in 3 meter per second square is focusing on a specific moment or focusing on a specific position. Okay, so from a graph over here, you can actually obtain some information as well. You know that this is a displacement against time graph. So if you look over here, this is the time taken to complete one single complete oscillation. So one complete oscillation here takes up 4 seconds. So we know that the time taken to complete one complete oscillation is the period. So from here, we can say that the period of this simple harmonic motion is 4 seconds. Okay, so these are the information that we know about this simple harmonic motion. So now let's move on to try and determine the velocity of the ball when the acceleration is 3 meter per second square. Okay, first we know that the maximum velocity here is equivalent to the amplitude multiplied by the angular frequency. This is what we know based on formula. Okay, but we are given the Vmax to be 3.2, but we don't know both the amplitude and the omega. But if you are given the period, you should always be alert that if you're given period, it's equivalent to saying that you already know the frequency. It's equivalent to saying that you already know the angular frequency. Because these three terms, they connect to each other. If you get one of it, that means you get all three of it already. So you need to know how to relate them. The period is 1 over f. The omega is 2 pi f. And omega is also 2 pi divided by the period. So all three of these are related to each other. You get one, you basically get all of it. So if you want to find omega, what you need to do is to find 2 pi over period. So 2 pi over 4. So if you do your calculation, you should be able to obtain amplitude of this simple harmonic motion to be equals to 32 divided by 5 pi meter. Okay, there you can write in decimal places, but if I write in fraction, right, the good thing is fraction means that you don't need to do any round up. So when you bring this fraction over to other calculation, your calculation will not suffer from any problem due to your round up. So that's why if it's possible to express things in fraction, in the middle of a calculation, if you're able to express things in fraction, express it in fraction, then you can minimize trouble due to you rounding up the answer. Okay, so now you know the amplitude, that means you have another one more new information already. So once you know the amplitude, you can unlock a lot of things to do. Okay, so we know that we are looking at the velocity of the ball for a specific position or for a specific moment where the acceleration is 3 meters per second squared. So what we can do is first find the x where the acceleration is 3 meters per second square. So this object here is undergoing simple harmonic motion at certain position, maybe here, maybe when x is equals to here, or maybe x is equals to here. At certain position, the acceleration will be 3 meters per second square. So if we know the position already, then we can find the velocity at that position, and that will be the answer over here. Okay, so how do you find x when a is equal to 3 meters per second square? Well, you know that acceleration is equals to negative omega square x. Okay, this is the relationship between the position and the acceleration. You know that you want your acceleration to be 3. So what's the position? Well, it's just a matter of calculation. So you are finding x. So if you key into your calculator, you should be able to get the answer of negative 1.22 meter. So what does it mean here is, if let's say here is negative 1.22, let's say this is negative 1.22, let's say this is negative 32 over 5 pi. Okay, let's say at negative 1.22, if you look at the acceleration at this point, you find that the acceleration is 3 meters per second square. Then if you continue its oscillation, then you find that at another point where x is equal to negative 1.22 as well, the acceleration should also be 3 meters per second square. At other position, you have different acceleration, but if you reach this position where x is equal to negative 1.22, you'll find that the acceleration is 3 meters per second square. Okay, so now what you need to do is just to determine whether what is the velocity at this position. If you're able to find a velocity, that will be what the question asking for. Okay, so your next step is to find the velocity, technically the x component of velocity, because this motion here is in the x dimension, so this is the x component velocity. Find the vx when your x is equals to negative 1.22 meter. So to do this, you have to use the equation Vx equals to plus minus omega square root of a square minus x square. Okay, so method of substitution now, 2 pi over 4 square root, the amplitude is 32 divided by 5 pi square, and the x is negative 1.22 square. So if you do your calculation, you should be able to get the answer of plus minus 2.57 meter per second. So this is the x component of velocity that you can obtain when the x is equal to negative 1.22 meter. Why is there a plus minus over here? Because if you look over here, if the ball is in this position, you know that this ball will continue to move downwards. This is what happens at later time. At later time, it will move to the negative direction. But if you look at the ball at this position, you know that at the next moment, this ball will continue to move upwards. So the ball at x is equal to negative 1.22 meter. At this moment over here, you'll notice that the ball will be traveling in the negative direction. So this one will be, the speed will be negative 2.57 meter per second. But for the ball at this position, also x equals to negative 1.22 meter per second, you see that this ball is actually moving upwards with the same speed. So this one will be upwards with a speed of positive 2.57 meter per second. So you know that the ball has at different moment it can either be moving in the negative direction or moving in the positive direction. But what they tell you here is just that x is equal to negative 1.22. They only tell you that acceleration is equal to 3 meter per second square. So both of these are valid position where the acceleration is 3 meter per second square. So we have to include both the negative answer and the positive answer for velocity in our answer. That's why the answer here has a plus minus, and you find that the magnitude is 2.57 meter per second square. That's why the answer for this question is plus minus 2.57 meter per second square. So that's how you solve this problem. There are also different ways to solve a problem. There's one where you can do, instead of finding x, you can find t, where acceleration is equals to 3 meter per second square. So in order to do this, what you need to do is you need to find the equation of x equals to a sine omega t. Then you can substitute in, it's 32 divided by 5 pi. Sine the omega is 2 pi divided by 4 t. Then you can differentiate this to get the equation of v. Then the equation of v will be, equation of v is 16 over 5. Is it? (16 over 5 cos 2 pi over 4 t). Then you can continue to determine the acceleration through another round of differentiation, and you'll find that the acceleration will be negative 8 over 5 pi sine 2 pi over 4 t. Okay, so now using this equation, you put in, this one is 3 meter per second square, then you get the time where the acceleration is 3 meter per second square. So once you obtain a time, what you can do is you can find the v when time is equals to blah blah blah. So you put the answer that you have inside here, then you use the equation v is equals to 16 over 5 cos 2 pi over 4, then you multiply the time that you obtain inside here, then you get the velocity. Okay, so this velocity here will also have the same answer as what you calculate over here. Just that if you are finding the time here, you need to be aware that there are many different moments where the acceleration is equal to 3 meter per second square. So your t here will not have one answer. There are many, there's technically infinite number of answers where the acceleration is equal to 3 meter per second square. So for different moment, you get either positive 2.57 or negative 2.57. Depends on which t that you are substituting in. There will be many answers for t where the acceleration is equal to 3 meter per second square. For the different t that you sub inside here, you get either positive 2.57 or negative 2.57. That's why the answer is plus minus 2.57 meter per second square. So that's how you solve question 17 over here. We have question 21. A wire of mass 40 gram is stretched between 2 points that are 100 cm apart. So 40 gram wire, then it's stretched between 2 points which is 100 cm apart. That means the length in between the 2 points should be 100 cm. And the tensional force is 80 Newton. Now you plug the wire, the standing wave is formed in the wire, and they ask you to find, if you triple up the tension, then you want to find the difference between the two fundamental frequencies. Okay, a very elaborate question. So let's try to draw a situation first. We know that we have a wire, then that is stretched between 2 points. So this is your wire stretched between different 2 points. The distance between these 2 points is 100 cm. Let's call it 1.00 meter. And this string here has a mass of 0.040 kg. Okay, and you are stretching it before you pinning it, then the stretch is 80 Newton. Okay, if you see they give you tension, right? and they give you mass and they give you length, right? You know that the mass and the length is for you to determine the mass per unit length mu. Then once you get the mass per unit length mu, you take the tension, divide by mu, then you square root it, you get the speed of the wave traveling on the wire. So you know that it will be related to speed. Okay, this is some intuition that you can build. You see tension, you see mass, you see length, you know that it will be related to the speed of the wave in traveling in the wire. Next, they tell you that this wire is plugged and it forms standing wave. And they ask, if you triple up the tension, make the tension 240 Newton, what will be the difference between the two fundamental frequency? So you are going to stretch the wire with 80 Newton of force, then you are going to plug it, then you observe the fundamental frequency, the frequency of the fundamental tone. Okay, then after that you increase the tension to become 240 Newton, then you plug again, then you observe the fundamental frequency, you take the fundamental frequency, then you find the difference between the two frequencies. That's the idea that we are going to explore over here. So how are we going to approach this question? Well, let's do it step by step. We know that we are interested in fundamental frequency. So fundamental frequency, what kind of wave will be formed will be, you have a string over here, and because the string is being locked at 2 points, okay, it's being pinned at these 2 points over here, that's why the string at the two ends should not be able to vibrate. If it's not able to vibrate, you should expect the standing wave to be always zero displacement at the two ends. So you know that both sides over here should be a node. So to make this pattern make sense, you know that in between nodes and nodes, there must be an anti-node. So this will be our standing wave fundamental tone pattern. Okay, to be more accurate, if you draw it out, it will be something like this. Okay, so again, this distance here, it's equals to L. L, it's 1.00 meter. And you know that it's equivalent to 1 lambda over 4, and the second one is also lambda over 4. Okay, the distance between the node and the next antinode, the antinode beside it, the distance between the node and the antinode beside it must always be lambda over 4. This is fixed. The distance between the antinode with the node beside it should also be lambda over 4. This is fixed. So you know that there are 2 times of lambda over 4 will be equals to the length of the wire over here. That's why you know that lambda over 2 should be equals to the length of the wire if it's for fundamental tone. So fundamental tone, we call it the first harmonic. That's why you can label it as lambda 1. Okay, once you reach here already, you know that you are interested in the frequency, you're not interested with the wavelength. So you can change it using this equation. V is equals to F lambda. So you can change lambda become V1 over. So it will become V1 over 2F1 equals to L. So if you rearrange the equation, you should get that the frequency should be equals to V1 over 2L. So this is the frequency for the fundamental tone of a stretched string. It's V, no need 1. Okay, the V is over 2L. This is the equation that we are going to use, and we have 2 cases. The first case and the second case. So for the first case, it's just F1 equals to V1 divided by 2L. For the second case, let's call it prime. The new frequency is equals to the new speed divided by the new length. Okay. So the speed we know is equals to T divided by mu 2L. This one will be equals to the new tension divided by the new mass per unit length divided by 2. Okay, we know that the mass per unit length should not change because you don't change the string. You don't change it from a metal string to a nylon string or whatever. It's the same string, so it should have the same mu. So you should expect that the new mu to be equals to the old mu and should be equals to the mass divided by the length, which is equals to 0.040 divided by 1.00. So this will be 0.040 kg per meter. Okay, the tension here, we know that the new tension should be equals to 3 times the old tension. So this one is something that you need to take note of. And the length here should not change because you're not changing where you pin the stretch string. It's still 100 cm apart for the 2 points over here. So the new length should be equals to the old length, should be equals to 1 meter. So now we have all the information that we need. What you need to do is continue by substituting the old value, substituting the new symbol to replace with the old symbol. What we need to do is, we know the new tension is equals to 3 times old tension. We know that the old mu is equivalent to the new mu. We know that the old length and the new length are the same. Okay, let's make it neater. Okay, so what we can do now is we can perform calculation of space. We want to find the difference between the two fundamental frequencies, so let's call it a change in frequency, and we take it as the new frequency minus the old frequency. So the new frequency, we know that it's square root of 3t over mu divided by 2l minus square root of t mu over 2l. So we can factorize out a lot of stuff. We can factorize out basically the whole thing over here, leaving square root of 3 minus 1 inside the bracket. Okay, we factorize out the square root of t divided by mu divided by 2l. We factorize it out. So we are left with square root of 3 from the first term, 1 from the second term. So now it's just substitution. Square root of t tension is 80 divided by mu, which is 0.040, divided by 2 times the length, 1.00. So multiply by square root of 3 minus 1. What will you get for the answer? You will get 16.37 Hertz. So this will be the difference between the fundamental frequency of the old case and the new case, the first case and the second case. So the answer is 16.37 Hertz. Okay, it's a relatively long-winded question, and I explain it in not the simplest way possible. I try to explain the idea of how you get the fundamental tone standing wave pattern and how you compare between the length and the wavelength by establishing the fact that the node and the antinode beside it should have a length distance of lambda over 4. So once we are able to find the compare between lambda and length, we change the lambda to become speed divided by the frequency. And from there, we just carry on, just do ratio question. Okay, so this is how we solve question 21. Let's move on to the next question. Question 23. A man is moving towards a wall with a source of sound in his hand. The frequency of the source is 50 Hertz. The speed of the man is 8 meters per second. So the man is holding a source of sound, maybe a speaker, and the speaker is producing a sound of 50 Hertz. Okay, a certain pitch. Now the man is moving towards a wall and it's moving with a speed of 8 meters per second. So now if the man sends 1 pulse of sound, means like beep, like 1 pulse of sound, what will be the frequency heard by him after the sound reflects off the wall? So the sound will travel towards the wall, get reflected and enters the ear of the man. So the man here will listen what kind of frequency. That is what we are interested to find. So let's draw a diagram to illustrate the situation that we have here. We have a man here, and this man is walking while carrying a sound source. Okay, so this sound source will produce a traveling wave and it will hit the wall, then it will get reflected back and you enter the person's ear. Okay, so we know that the frequency of the sound source is 50 Hertz And we know that the person here is traveling with 8 meters per second towards the wall. And the speed of the sound traveling in the medium should be 330 meters per second. So that is what we know about the situation over here. So we know this will be related to Doppler effect, but let's try to think about the situation more clearly. Okay, so the person is moving towards the wall. So the sound source is moving towards the wall. So let's treat right now for the first part. Let's treat the person holding the sound source as the sound source. And let's treat this wall here as the observer. So the man, the sound source, the man will be the source, then the wall will be the observer. In this case, we know that the source is moving towards observer. Okay, so let's try to determine what is the frequency, the apparent frequency heard by the wall if the wall is able to hear something. What will be the frequency heard by the wall? So we'll use Doppler effect. The apparent frequency that will be received by the wall will be equals to V plus minus VO V minus plus Vs frequency. Okay, so let's try to recap a bit. This V here will be the speed of sound. This V here will be the speed of the observer. This V here will be the speed of the sound source. This F here will be the frequency of the sound produced by the sound source. So we know that for this case, our observer is stationary, so we can change this to become a 0. So if we change it to become a 0, we can modify our equation to be V divided by Vs. We are going to fill in the symbol now. So should we put a negative or a plus over here? That depends on our understanding. Okay, I have a video about Doppler effect, teaching my way of calculating Doppler effect. Okay, it depends on some physics understanding, but essentially you should be able to get it. Okay, so we know that the sound source is moving towards the observer. So know that the distance between the sound source and the observer is decreasing. If you see this kind of situation, you know that the apparent frequency should be higher than the frequency produced by the sound source. Okay, it's not because the distance decrease. Okay, it's because of the relative motion. But there's a pattern that you can see. The pattern is if the distance between the sound source and the observer is decreasing, then you know that the apparent frequency should be higher than the frequency produced by the sound source. That means this F subscript A here will be larger than the F over here. If you want to make our answer larger than our input, if you want to make our output larger than our input, what should we do to the denominator over here? Should we make the denominator smaller or larger so that we can get FA to be larger? If you want FA to be larger, you want to make the denominator smaller, right? That's why to make it smaller, you should put a minus. If you put a plus, it becomes larger denominator. Larger denominator will cause FA to be smaller than F, which is what we don't want. We want FA to be larger than F, therefore the denominator must be smaller than the numerator technically. Okay, so now we can do our substitution. We know this is 330 minus the speed of the sound source 8 times the frequency produced by the sound source 50. So if you calculate all this, you should be able to get an answer, but I will not calculate it. I just leave it like this. Okay, so the wall will be receiving the sound wave with this frequency over here. So if the sound wave reflects from the wall, it should be reflecting off the wall with the same frequency as the frequency received by the wall. If I receive a sound wave with a certain frequency and I reflect it back, I should reflect with the same frequency. That is just law of reflection actually. So you know you are going to reflect with the same frequency. So now we will look at the second part of the journey, second part of the situation in which the wall will now become the source of the sound. So the wall is reflecting off the sound. So the wall is now the sound source. It is producing the sound. And now who is listening to the sound? The man is listening to the sound. So now the man will be the observer. So why do I always mess up this? The man will be the observer. So now look at the situation. The observer is now moving, that's right here. The observer is now moving towards the sound source. Okay, the scenario never changed, but the role changed. In the first part of the situation, the man is the sound source, the wall is the observer. Okay, but now you continue the same scenario, but after the sound wave reflected off the wall will now be the sound source, whereas the man will be the observer. So they switch their roles right now. Okay, and for this situation, the observer is moving towards the sound source. Okay, so we are again going to use Doppler effect to determine what is the frequency of the sound wave listened by the man over here. So we are going to use the same equation. But here's something interesting. We have already said that our frequency here is the frequency produced by the sound source, and this is the apparent frequency, which is the frequency received by the wall. We say that now the sound source will be the wall, so the wall will be reflecting off the sound wave. So the producer of the sound source, the producer of the sound wave is now the wall, and the frequency of the sound wave reflecting off the wall is this value over here. That's why what we should change here is the frequency produced by the sound source, or the frequency produced by the wall, or the frequency reflecting off the wall should now be the FA that we have determined earlier. Whereas the F apparent that will be listened by the observer here, we change the symbol to be the new apparent frequency listened by the man over here. Okay, we are changing a bit the equation to fit the second part of the situation. So now we know that the observer is moving, not the sound source is moving. So the sound source is stationary, so this one will be 0. So our equation will be VO divided by V. F apparent. So F apparent here, I'm going to substitute in 330 minus 8 times 50. What I do is I just bring what I have over here over here. So now I also need to determine whether here should be the positive sign or a negative sign. Well, again, the distance between the observer and the sound source is getting smaller. So if the distance between the observer and the sound source is getting smaller, you know for a fact that the apparent frequency should again be higher than the frequency produced by the sound source. So this FA prime here should be larger than FA. So if you want to make FA prime larger than FA, what should you do to the numerator? Should you make the numerator larger or smaller? If you make the numerator smaller, then you cause a smaller answer, right? If you make the numerator larger, you cause a larger answer. That's why you need to make the numerator larger in order to produce a larger FA prime. And the FA prime will be larger than FA. So to make it larger, you need to use a plus. Oops. So that's why you use plus. So now you perform a substitution. 330 plus 8 divided by 330 times 330 minus 8, 50. So you know that these two can cancel each other out, and you perform your calculation, you should be able to get 52.48 Hertz. And that's why this is the answer. If you read in different books, they might have different kind of equation being given, and you might have seen equation like this before. FA is equals to V plus the V of the man divided by V minus the V of the man F. You might have seen equation that is being designed like this, but this is actually coming from coming from this equation over here. If you cancel this out, then this will be V plus V observer. Down here will be V minus V of the sound source. So if you combine them, this will be the equation that you get. Then you can sub in the frequency of the actual sound source. The 50 Hertz over here, you can sub it inside here. Then you can sub in 330, 330, 8 and 8. Then what we'll get here will be the frequency listened by the man himself. So this is a simplified way of doing things, but I'm here showing you that how this equation comes into place is by doing the first part, determine the apparent frequency received by the wall. Then know that this apparent frequency will be the frequency reflected off the sound wall. So you come back to the man and it will be listened by the man over here. Okay, so this is how you solve a Doppler effect if it involves some kind of reflection. Remember, if there's a reflection, the received and the reflected wave should have the same frequency. That's the idea. Okay, so that's how you solve question 33, and that is all the question that I want to discuss for pre-PSPM 1 set 2 for SP015. Thank you.